So fine, just recollecting of our Western's class. So we are in the chapter of dielectrics and capacitance. Okay, so here we are seen with basic introduction part yesterday. Why we are concentrating on dielectrics before having an idea on capacitance. And since capacitance is on current dependent, we have gone with the basic definition of current. Basic definition of current. So later we have seen with current density. Okay, so current density, and finally with the type of flow of current. With the type of flow of current, we have classified the current densities into three types. First one, convection current density. Second, conduction, and the third, displacement. And we have got an idea what do you mean by convection, what do you mean by conduction, and what do you mean by displacement by using another other concept of transfer of heat. So by way how the heat is being transferred from one object to another object, in the same way we have related the flow of current, uh, whether it is flowing in the direct contact or by the means of medium. So if you are having the direct contact, then we are going to call it as a conduction. And if it is passing, if the flow of current is through the medium, then it is convection. And in case of semiconductor devices, semiconductor material, okay, so where the flow of current is because of diffusion of electrons and holes. Okay, so there we are going to call it as a displacement current density. That we will see later. But as of now, in yesterday's class, we have seen about what do you mean by convection current, and we have derived for convection current density, so that we have taken one vacuum tube, and this is the schematic diagram, and later we have proceeded with the derivation, and finally we have got this expression. So where J is nothing but the current density, and rho V is what? So volume charge density, and capital V. So this capital V is nothing but what? Velocity. So don't get confused with the small v and capital V. So here small v is the volume and capital V is the velocity. Okay, so this is about a small recollecting of our yesterday's class. And now we are going with the second current density. So that is called as conduction current density. Okay, so conduction current density, here the flow of charges in a conductor. In a conductor. Okay, so the flow of charges in a conductor. So as of you know, so for let us take a copper wire. We know that a copper is a very good conductor of electricity, because here the copper is having more number of free electrons. So it is having free electrons. So whenever you are going to apply the potential between these two ends, so because of this electromotive force which we have applied between point A and point B, so these electrons will be mobilized and they are going to be excited, so that they are going to travel from higher potential to the lower potentials. Okay, so now because of that, now we are going to call them as what? Flow of electrons or flow of charges. Those charges are having a of negative charge, which is nothing but minus E. Suppose if you are having in a conductor, if you are having n number of electrons and each electron is is of charge of minus E, then n into minus E will be the total amount of charge that is flowing within that conductor. So here this type of flow of current inside a conductor is called as what? Conduction. Now we are going to derive the current density for this type of flow of current, so which is called as conduction current density. Since we are talking with respect to the electrons, first we will write the force equation. First we will write the force equation for a point charge. Point charge is nothing but a single electron. So if you multiply this single electron with n, we can relate for total conductor. So therefore, we will start with a single electron and later we will relate it to the number of electrons. So force equation for a point charge, already we are very much familiar with that. So what is that? So force on a point charge given by Coulomb's law. So very well known equation, that is F is equal to Q into E, where Q is nothing but the charge of electron and E is nothing but the electric field intensity. So we know that since we are dealing with the electron, electrostatic fields are flow of electrons. So for an electron, what will be the charge? For an electron, the charge is Q is equal to what? Minus E. So now just modifying for the above equation, that is F is equal to Q into E, we are going to replace the value of Q with minus E. So therefore F is equal to minus E into capital E, which is our equation 1. Okay. Now we know that, so whenever you are going to apply the potential difference between the point A and point B, between the two ends of the conductor, these electrons are flowing with some, these are of what? Moving particles. Now they are moving, and definitely this electron is having some mass. Any particle which is having some mass will experience some force, and that force is given by Newton's second law. So very much familiar for us. So Newton's second law, which is given as what? F is equal to m into A. F is equal to 1 m into A. So whenever, if you are having any particle which is in movement, whose that particle is having some mass m, definitely it will have some momentum, and that momentum of force is given by F is equal to m into A. Here we know that m is nothing but mass of an electron, and A is nothing but the acceleration. A is acceleration. So what is the basic definition of an acceleration? How to define an acceleration? That is nothing but what? Rate of change of velocity. We know that. It is we know that basic definition in our lower standard. That is A. Acceleration is, how to define it? Rate of change of velocity. Simply to say, that is nothing but what? Velocity per time. So rate, in the sense I told in the earlier class, that is nothing but we are going to define with respect to time. So rate of change of velocity is nothing but velocity per time. But here we will make some correction for this definition for this application. That is what? Conduction current density. What is that means? Why we are doing that correction also I will explain now. So A is equal, but instead of writing the velocity here, we will write it as drift velocity, and instead of writing the time here, we are going to take it as average time. Okay, why we are writing drift velocity and why we are taking average time is the important concept that was behind, that we have to understand. See here, I'm going to tell now. Suppose if you are having one conductor, so this is a copper conductor. I told that electrons, they are very free to move. They are moving from, they are like this. So which are available for this entire conductor, which are present entire conductor. Now what we are going to do? So we are going to apply the potential between these two ends. Because of this potential, okay, so now these electrons will start moving. with some velocity. So let us consider one electron. So let us take this electron. So this electron will move with some velocity. By moving with some velocity, it will get collide with the other electron which is traveling in front of it, which is traveling in front of it. Okay, so likewise, so suppose if this electron got collide with this electron, after collision, so its path is going to be changed like this. So we know that, for example, if you are having one car is moving some with some velocity. Okay, so if this car is moving, and definitely if it got hit with another car. Okay, so if it got hit with another car, definitely it will change its direction of travel, its direction of travel. So similarly, here also, when this electron, if it is getting collision with the nearby electron, this electron will deviate its path. It deviates its path. Now in this path, suppose if there is one more electron, again it is going to collide with this electron, and again it is going to deviate the path. So again it is going to collide with this electron, again maybe it changes direction. So likewise, it will have multiple number of collisions, and finally it will reach the final point of B. Okay, so actually what is happening actually, so for a single electron, the direction should be the path, the actual path should be straightforward. So because of many number of electrons which was present inside this conductor, so the actual path is going to be uh, changed, and it is going to have some other path like this, and finally it is going to reach this point B. And because of that, see, because of that, this from here to here, if this is time t, and for this electron this t has been changed, it has been increased because of that, because of the collisions. So for this electron, so similarly there is one more electron, so definitely it will also got collisions with some other electrons, and also it will also travel some other direction, and it is having some time t2. So for this electron, let it be T1. For this electron, let it be T2. For this electron, let it be T3. And for this electron, let it be T4. And finally, they are reaching this point B. So because each and every electron, they are having different time of travel. They are having different time of traveling. Different time of travel. What we are going to do? So we are going to take the average value of all the electrons, the average value of all the electrons. So therefore here I am writing as what? Average time, instead of writing the time. Since the electrons will get collide with each other, the actual time for every electron will be differed with other electron. So therefore the time, as they are having a different traveling time, so we are going to take what? Average time here. And next, what about drift velocity? Drift velocity means, I told that, suppose you take one cricket ball and you take one more cricket ball. So if you hit both of the balls, so definitely they will get deviated. They are going to get deviated. So earlier this is velocity, and now after hitting, now we are going to call this as what? Drift velocity. So we are going to call it as drift velocity. So see here, inside this conductor also, electrons are traveling by colliding with each other. While colliding, they are going to deviate their actual path because of hitting, and after hitting they are going to deviate. So here this deviation is getting what? Drift velocity. Okay, so this drift velocity. So therefore here in the numerator is the velocity, we are writing as drift velocity. In the denominator, instead of writing with time, we have taken average time. Okay, so that is the important concept. So therefore here, what will be the value of acceleration? A is equal to what? So drift velocity divided by average time. Drift velocity by time. So that is equal to, drift velocity is given by capital V, and time we are going to average time I am representing with tau. Okay, so with the tau. Now I am replacing this value of a, that is equal to v by tau, in this equation, in the equation of f is equal to ma. F is equal to ma. So since we have f is equal to ma, whatever the value of a is here, so m into capital V divided by tau, capital V divided by tau. So which is our equation number 2. See here, so equation 1 dealing with the electron force, and this is also the mass we have taken for electron, and the acceleration is also we are talking with respect to electron. So this force is also for the force experienced by the electron because of Newton's law of force, Newton's second law. And so therefore we can relate equation 1 and equation 2. So what is our equation 1? The equation 1 is f is equal to small e into capital E. So that is equal to minus E into capital E. And what is our equation 2? Equation 2 is equal to mv divided by tau. Mv divided by tau. So from this equation, I am writing the value for v, which is nothing but the velocity. So minus E capital E tau whole divided by m. Okay. So whole divided by m. So let it be equation number 3. Okay, since we are talking with respect to the conductor, okay, since we are talking with respect to this conductor is having some volume, and inside this electrons are there, so therefore it is having some volume charge density, so which is given by rho suffix v. Okay, rho suffix v. Now I am writing what? Volume charge density. Volume charge density, which is given by rho v. Okay, so rho into v given by formula, that is equal to what? Total charge per unit volume. What is total charge here? So here I have written total charge inside inside what? Inside a conductor, the total charge is given by what? N into minus E. N into minus E. So therefore, total charge is equal to what? Minus N into E. What is unit volume? Unit in the sense 1. Okay, so unit volume is 1. So therefore, what will be the value of rho v? Rho v is equal to minus N into E. Okay, so rho v is equal to minus N into E. Now we have to write for current density. Okay, so current density. So current density for this, which is represented by J. Earlier already we have derived one equation for current density. What is that equation? So this is the equation. So J is equal to rho v into so this is equal to what is rho v? Rho v is equal to this one minus N into E, and what is V? So V just now we have got from equation 3, that is minus E into E tau by M, minus E tau whole divided by M. So minus into minus plus E into E, we will get E square. So N E square capital E tau divided by M. Now rearranging this equation, N E square tau whole divided by M multiplied by E, which is equal to J, and rewriting this equation, J is equal to sigma into E. So where sigma is equal to what? N E square tau whole divided by M. So this is very important equation for us. Why it is important means, see here sigma. What is here J? J we are talking with respect to conduction. Conduction current density here. So whatever the sigma here we have got, it is called as conductivity. Conductivity which is reciprocal of resistance. Very, very much important. Okay. So conductivity, which is the reciprocal of resistance. More the conductivity value, more it is called as the conductor. Okay. So now see here one important conclusion that I am going to make from this expression. With that conclusion, they are going to ask one question for you. They are with the conclusion only, with respect to the conclusion only, they are going to ask the question. In your examination, they are not going to ask derive the expression for conduction current density. They will ask in another format, in another form. So with that conclusion, you can understand what you should write the answer. Okay. So here you have got J is equal to sigma into E. Sigma into E. J is sigma is nothing but conductivity. I told, but reciprocal of resistance means, can I write it as 1 by R, where sigma I can relate with what? I can relate with 1 by R. Okay. Sigma I am relating with 1 by R. Now what is J? J I have related with current density. So J is related with the current. And what is E? E is, see here, E is equal to minus of del into V, which is derived from what? Maxwell's second equation. So from here, E is directly related to what? V. What is V? V is nothing but potential or voltage. So therefore, E directly related to V. So which is nothing but what? Potential. So here J is current. Current is equal to 1 by R. Sigma, in place of sigma I am writing as 1 by R, and in place of V I am writing it as potential. So in which form it is there? I is equal to 1 by R into V. So if you rearrange this, V is equal to what? I into R. So what is this equation? Have you seen this expression before? V is equal to IR. What is that equation?
Ohm's law, sir.
Ohm's law. Very good. So this
Yes,
is
sir. Ohm's law.
So therefore, we are going to call the equation J is equal to sigma into E as point form of Ohm's law. Okay, so that is why I told this expression is very much important for us. Okay, so J is related to current, sigma is related to resistance, and V is related to V, which is in the form of Ohm's law. So therefore, J is equal to sigma into E. We are going to call it as what? Point form of Ohm's law. So in your examination, they will ask us what? Obtain the equation for point form Ohm's law in point form. Like that they will ask. At that time, what you have to write? You have to go for the derivation of conduction current density. Okay. So don't think that we have not gone with this derivation of point form of Ohm's law. So J is equal to sigma into E itself. It is called as what? Point form of Ohm's law. Why means here I have given the reason. Okay. So this is all about what? Conduction current density. So earlier we have seen convection current density, and now we have seen conduction current density. Both the cases. Okay. So earlier we have got J is equal to rho V into V, which is called as convection. And now we have obtained the equation what J is equal to sigma into E, which is called as conduction. So in some of the examination, they will ask what obtain the or derive the expression for conduction current density as well as convection current densities. Okay, so for an essay type answers. So therefore, at that time you have to write both the equation. So depending upon the type of question, you have to proceed with the answer. Okay, so that is the very much important point. So just wait, I would like to